Another day, another story. The concept of an atom inside an atom isn't possible in the conventional sense based on current scientific understanding. Atoms, as fundamental units of chemical elements, consist of a nucleus, made up of protons and neutrons, surrounded by electrons. These components are defined by specific rules and structures governed by quantum mechanics. Welcome to Bose-Eminent channel. The idea of having a complete atom inside another contradicts the established structure and behavior of atoms as we understand them. Subatomic particles, atoms themselves are made up of smaller particles, protons, neutrons, and electrons, and protons and neutrons are made up of even smaller particles called quarks. These layers of substructure show that within atoms, there are smaller components, but they are not atoms in themselves. Nuclear physics experiments, in experiments where high-energy particles are collided with nuclei, as in particle accelerators, smaller particles can briefly exist within the spatial region of the nucleus. However, these are transient phenomena and don't constitute stable atoms within atoms. Quantum dots. In a broader metaphorical sense, quantum dots are sometimes playfully referred to as artificial atoms. These are nanoscale semiconductor particles that can trap electrons in a confined space, allowing them to only occupy discrete energy states similar to electrons in an atom. While this doesn't represent an atom inside another atom, it does echo the concept of creating atom-like behaviors on a different scale. Electron shells and orbitals, while not atoms within atoms, the arrangement of electrons in shells and orbitals can sometimes be viewed as structured layers within an atom, each with its distinct properties and behaviors. Virtual particles and quantum foam. In the bizarre world of quantum mechanics, the vacuum of space is anything but empty. According to quantum field theory, space is teeming with virtual particles that spontaneously appear and disappear. These particles exist for such a short time that they can't be observed directly, but their effects, such as the Casimir effect, can be measured. In this context, one might imagine scenarios where virtual particles momentarily emerge within the spatial boundaries of an atom, albeit not forming a stable atom within an atom. Quark-gluon plasma. Another intriguing area of research is the study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang, where protons and neutrons are broken down into a soup of quarks and gluons. This plasma can be recreated momentarily in particle accelerators, such as the Large Hadron Collider, by colliding nuclei at high energies. Bose-Einstein condensates. Bose-Einstein condensates, BECs, represent another state of matter where atoms are cooled to temperatures very close to absolute zero, causing them to occupy the same quantum state and behave as a single quantum entity. This phenomenon could metaphorically be seen as many atoms acting as one, suggesting a unified behavior that could be poetically described as atoms within an atom, albeit not in a literal sense. Here, individual identities of atoms blur, illustrating quantum effects on a macroscopic scale. Quantum entanglement. Quantum entanglement is a phenomenon where particles become interconnected such that the state of one, no matter how far apart they are, instantly influences the state of another. In a complex atomic system, if you were to entangle certain subatomic particles from different atoms, their interdependent properties might create a system where boundaries between individual atoms become less distinct. While this doesn't create an atom within an atom, it hints at a level of interaction and connection that transcends classical atomic boundaries. Advanced theoretical models. On the cutting edge of theoretical physics, concepts like string theory and loop quantum gravity attempt to describe the universe at the most fundamental levels. These theories suggest structures and phenomena at scales and in forms far beyond our current observational capabilities. Expanding on quantum dots, atom-like behaviors in controlled conditions. Quantum dots, often referred to as artificial atoms, provide an excellent demonstration of how atom-like properties can be engineered on a nanoscale. These semiconductor particles confine electrons in 3 dimensions in a space so small that their quantum properties become dominant. The electrons in quantum dots exhibit discrete energy levels, similar to those seen in electrons orbiting an atom, which can be precisely controlled by changing the size of the dot. Emergent phenomena in condensed matter physics. In materials science and condensed matter physics, emergent phenomena occur when a system exhibits properties its individual components do not possess on their own. A classic example is superconductivity, where certain materials conduct electricity without resistance at very low temperatures. The cooperative behavior of electrons in a superconductor suggests a collective state that could be seen as an atom of a higher order, composed of numerous smaller particles acting in concert. These emergent behaviors challenge our understanding of how properties manifest at different scales, suggesting that under the right conditions, atoms could indeed form structures and exhibit behaviors that are not evident from their isolated states. Probing the nucleus, hypernuclei, and exotic matter. The atomic nucleus itself is a fascinating frontier of study, particularly with the creation and examination of hypernuclei. These exotic atoms contain one or more hyperons, particles containing strange quarks, in addition to the usual protons and neutrons. The study of hypernuclei gives insights into the interaction of strange matter, potentially applicable in understanding the conditions inside neutron stars where strange quarks might form a substantial part of the matter. Virtual particles and the vacuum fluctuations. Further into the quantum realm, the concept of virtual particles and vacuum fluctuations paints a picture of space filled with a seething froth of particle-antiparticle pairs popping in and out of existence. This quantum foam suggests that even the vacuum is not empty, but a dynamic, bubbling sea of activity that constantly influences the behavior of particles. In high-energy environments, such as near a black hole, these fluctuations might become extreme, suggesting environments where our conventional understanding of particles and atoms breaks down. The frontier of quantum gravity. On the most speculative frontier, theories of quantum gravity aim to meld the principles of quantum mechanics with general relativity. Here, concepts like atoms and particles might take on new meanings. In theories such as string theory, the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. The vibrations of these strings determine the type of particle, their interactions defining the universe's structure at the most fundamental level. Conclusion: each of these areas reveals the profound complexity and subtlety of interactions on atomic and subatomic scales. While the notion of an atom within an atom isn't feasible in a straightforward sense, the evolving understanding of quantum and classical interactions in physics continues to challenge our perceptions of what is possible, encouraging deeper inquiry into the nature of matter and reality. These explorations remind us that the universe is far stranger and more interconnected than it might superficially appear, with much left to uncover and understand. Thanks for watching. Request you to subscribe the channel.